everybody. So today I'm going to do a new chapter, that is magnetisms and matter, right? So before I start this chapter, let me do a brief introduction about the chapter, that is magnetisms and matter, right? So last chapter we talked about magnetisms that mainly related to current carrying conductors, all right? So how current carrying conductor produce the magnetic fields. Alright, so now this time what we are going to do is we are going to talk about the arc magnetisms and the magnetisms which are related to matters. Alright, so the study about these magnetisms was started maybe 3000 years back. Alright, so the term magnets was derived from one of islands in the Greeks. What happened is that the place called Malaysia, Magnesia, where you find so many magnetic ore, right? So maybe you might have heard about that story, right? Talk about the shepherd. Normally, maybe a long back, people used to wear wooden shoes and they put nails. All right. So what happened is that when he go for walk, what happens is his feet gets stuck. Why? Because the magnet attacks his the nails, right? So this phenomenon, right, that is the magnetic properties, right, that stucks his shoes, right, was found 600 years 600 BC, around 600 BC, right? And also you might have heard about something like, you know, the people maybe 600 years BC around, right? When you go in that area, you find so many small stones get attracted toward the shoes, and then that is what we call as a lodestone, something like that. And this kind of stories let us study what we call as magnetisms. All right. So, and then one very significant study about magnetism is magnetic compass, right? Maybe 2000 years back, people could able to know the directions with the help of magnetic compass. So the entire concept about magnetic compass is based on what we call as magnetisms. All right. So now let me give you a very fundamental or basic ideas about magnetisms. That is, maybe you have done this in a lower class. So what happened? Maybe you have done that simple experiments. If you let bar magnets very far from each other, let freely suspend, and what you will find is all the bar magnets, all right, irrespective of initial conditions, all the bar magnets, after some time, all the bar magnets, they suspend or they align themselves along a north-south direction. That means all the bar magnets align in one particular direction. So that means this tells us an idea that there is some force which lets all the bar magnets to align in that particular direction, and that the later people came to know that force or that force which lets all the magnet to align in a particular direction is none other than our earth magnet. That is what we call as earth magnetism. Alright, so when a bar magnet is freely suspended, it points in a north-south direction. The tip which points to the geographical north is what we call as north pole, and the tip which points to the geographical south is called a south pole of a magnet. And then one more thing we have studied is that when I put a north pole to the north pole of another bar magnet, you see a repulsion. So there is a repulsion. Like pole repel each other. And then when I bring a north pole and south pole, they attract each other. That is what we call, this is a fundamental of property of magnets. And then one more important thing is, when we talk about bar magnet, when we talk about magnet, it has two poles. We call it as a south or north, And we say that these two poles are inseparable. We cannot separate North Pole from South Pole, unlike electric dipole. When we talk about electric dipole, I can separate a positive charge from negative charge. However, when we talk about the magnetisms, these two poles, North Pole and South Pole, you cannot separate. Why? If you cut, the North Pole will appear or South Pole will appear, right? So we cannot isolate North Pole and South Pole of a magnet, and then therefore the magnetic monopole do not exist. I'm sorry, this exists, right? And so maybe we talk about bar magnet, and bar magnet is one of such an example, right? So it is possible to make a magnet out of irons and its alloys. So this is what we talk about bar. So these are the one very important or commonly known ideas regarding magnetisms. So this is what we find. All right. So this you might have seen this thing in a lower class. Bar magnet gives magnetic fields, and you can visualize magnetic field, and you can show a magnetic field by using iron dust, iron filing. If you put iron filing, this kind of pattern you are going to get it. So this is going to be a North Pole, and this is going to be a South Pole. You find more iron dust, iron filings accumulate at the two poles. That shows that magnetic fields are stronger at the two poles, right? And this is this pattern of a magnetic field, and then we visualize this, and we try to represent in terms of magnetic field line. So these are the examples. And then one, right? Maybe if you go higher classes, you will see the significance of arc magnets. All right. So this is what, right? So this is our arc. This is not there in syllabus. Just for your interest, I'm giving you, right? Sun give rise a solar wind, that is some ionized gas, right? So what happens is that since Earth having magnetic fields, we say that the magnetic fields deflects moving charge. All right. So this solar winds is nothing but composed of electric charge. So this magnetic field will not let some solar wind to enter into Earth's surface. Why? Because it deflects the magnetic ions, right? So therefore, magnetic field act as a blanket. All right. So that this will help us to enter. All right. This will prevent, right, solar wind to enter to this to Earth's surface. So this is one very significant. This is the significance of. So Earth is a unique. Why? Because it has a unique magnetic fields, and then field doesn't allow solar wind to enter into Earth's surface. So these are the examples, right? And then now what we are going to study this chapter in these years. So many topics are deleted from this chapter. All right. So now what I'm going to talk about is now magnetic field lines. All right. This is very similar to electric field lines. A few, one small difference is there. Otherwise, all same. Right. This is what I have. Right. So last time, just now I have shown you magnetic the patterns, right, are formed by iron filing or iron dust, and these patterns can be written in a field line, right? So this is what we call as magnetic field lines. So we say that, and then this is very similar to electric field lines, right? So what happens is that magnetic fields enters into a south poles, and magnetic field goes out from north. This is the one very important differences, right? And therefore, the magnetic field forms a loop. Close, look at here. This is a loop, right? This is a loop. All right. And why magnetic fields are stronger at the two poles? You see, magnetic field lines are crouched. The closer at the two poles, therefore magnetic fields are stronger. And the direction of magnetic fields are again given by a tangent at any point, right? Say, what is the magnetic field at this point? Magnetic field at this point is given by tangent, right? What about magnetic field at this point? Given by tangent. Magnetic field at this point. So this tangent at any point on a field line represents the direction of magnetic field, right? This is very important, right? So these are the property, right? These are the property of magnetic field lines. Magnetic field line forms a continuous closed loops. Electric field line doesn't form a continuous closed loop. Magnetic field line, why? Because unlike electric dipole, magnetic field line begins from positives and ends at the negative, right? And the tangent to the field line at a given point represents the direction of the net magnetic field at that point. So the magnetic field line, the direction of magnetic field line is tangent at any point, which I have shown just now, right? The larger the number of field lines crossing a per unit area, stronger is. That means if the closer the field lines are, stronger the magnetic field is. If the magnetic field lines are not close to each other, then field is not strong, right? Then magnetic field line do not intersect each other. All others are same except first points, right? This is very important. That is property of magnetic field lines. Property of magnetic field lines. All right. Now we talk about. Let's say we will find out the differences between an electric dipole and magnetic dipole. This is an electric dipole, right? So when we talk about electric dipoles, negative goes into and positive it comes out, and then electric field always comes to this, right? This is not a closed loop, right? Look at here, electric fields never form a closed loop. Negative to positive to negative, right? Then it goes out, goes into, right? So a closed surface represented by I, all right? Number one. The number of field line leaving is equal to number of field line entering the surface, so it close George. However, like let's say this, if I'm talking about this, all right. However, look at here. However, in the same figure for surface 2, this is surface 2. This is the surface 2. When you look at the surface 2. There is a net outward flux since it does not include the net positive charge. Look at here, this is right. So this is, you see the electric field lines are going out. So there is a net flux going out. In this case, the number of field line entering is equal to number of field line leaving, right? So this flux is going to be 0. This flux is not going to be 0, right? So this is for electric, just small recapitulations. And now look at here. This is for solenoid and this is for bar magnets, and this is the magnetic field lines. So bar magnet and solenoid magnetic fields are identical. Magnetic fields are identical. They are identical to each other, right? They resemble each other, right? So what happened is that, look at here, both the cases 1 and 2, all right, 1 and 2, both the cases. Look at here, the Gaussian surface, right? Alright, both the cases, right? Look at here, this, when North Pole is coming out, South Pole goes into it. North Pole is coming out, South Pole goes into it. And then, look at here, look, you see a closed loops are forming. Okay, you see a closed loops are forming. You see like this. Closed loops are forming, right? This is what we talk about. If a closed loop forms, right, these closed loops are formed. Now, if you choose any closed surface, if you choose any closed surface, then magnetic flux would be 0. Magnetic flux would be 0. Why? Because the number of a magnetic field line entering the surface is equal to the number of field line leaving the surface. So therefore, this is always flux is always 0. So therefore, the concept about Gaussian law, right? We'll discuss this just now, right? The Gaussian surface by represented by 1 and 2 in a figure number A and B. Both the cases visually demonstrate that the number of field lines leaving the surface is balanced by number of field lines entering it. The net magnetic flux is 0 for both the surface. So that means if I choose any closed surface, whenever we talk about magnetic field lines, we talk about magnetic field lines, if we choose a closed surface, every time number of field line leaving the surface is equal to number of field line entering the surface, so therefore net flux is going to be 0, right? Net flux is going to be 0. So therefore this is what we talk about. Let's say if I give you an example, right? This is the bar magnet. This is the bar magnet. This is the bar magnet. And if I choose a closed surface like this, this is a closed surface if I choose. And look at here, these are the field lines, you will get it, right? These are the field lines. So what you find is a number of field lines entering this closed surface is equal to number of field lines leaving the closed surface. That indicates that, this implies that net flux is going to be a 0. So this is very important. This is the one where you find the differences, right, between electric dipole and magnetic dipole. And this implies that in case of magnets, two poles cannot be separated, right? So having this, I'll discuss what we call as a Gauss's law, right? So when we talk about Gauss's law, we talk about a total flux. Total flux is equal to magnetic fields into just write this, right? Area, right? This is what we have, total flux. So total flux in case of Gauss's law is always 0. And this is the closed Gaussian surface. And this is magnetic field, right? So this is always 0, right? So in another word, I can write also like this. This is B 0, right? The reason is that whenever we talk about this magnetic fields, it always form a closed loop. When it form a closed loop, then number of field line entering is equal to number of field line leaving the surface. So this is what we talk about. Alright. So this is what we talk about, Gauss's law. Alright. So Gauss's law, in case of magnetism, Gauss's law is 0. I can figure out this, right? Let's say this is going to be, flux is going to be, when I can write like this. Mu naught. Alright. So normally when we talk about a flux is going to be QE net, right? Enclosed, right? I say enclosed divided by epsilon naught. When we talk about this, 1 by epsilon naught corresponding to mu naught. Alright. So mu naught, magnetic charge. Let's say this is magnetic charge. And I say the net magnetic charge. Let's say this is a Q, M stands for net magnetic charge. And net magnetic charge is always 0. Net magnetic charge, why? Because net magnetic charge, you cannot isolate North Pole and South Pole. So therefore net magnet must be 0. So this is going to become 0, right? This is going to become 0. So which implies that flux is 0, which implies that the flux is 0. So this is one very important, right? So having this, I would like to give you analogy between electric and magnetic dipole, right? And before that, this also has been removed from our chapter, that is resemblance between a magnetic bar magnet and a solenoids. However, what I'm going to do is, whenever we talk about dipole or bar magnet, when we keep a bar magnet in external magnetic fields, bar magnet or magnetic dipole, let's say bar magnet is a magnetic dipole, right? Magnetic dipole in external magnetic fields in a uniform magnetic fields, then it experiences a torque. This is going to be this experience a torque. How much torque? This is the torque experience. All right. This is the And B is the magnetic moment of a bar magnet. This is the magnetic moment of bar magnet. Magnetic moment. And B is magnetic fields. Now what I'm going to do is that, what about potential energy store, right? What about potential energy store, right? So potential energy store to move through a small angle theta would be equal to m top theta d theta. That means I rotate through a very small angle, and then rotational potential energy is torque into theta. And what is the torque? So torque is going to be mb sine theta d theta. So the potential energy store would be equal to minus cos theta, right? This is what we have, right? So this is going to be, and this is what we have. This is the potential energy store. This is the potential energy store when you keep a bar magnet in an external magnetic field, right? So this is what I have. Now I would like to bring electricity or electrostatics and the magnetisms, right? When you talk about electrostatics, this is the constant, right? Electric permeability. When you talk about magnetism, this is going to be a constant. And then when you talk about dipoles, this is going to be a dipoles to a Q, P caps. When you talk about magnetism, this is talk about IA. All right. And then when we talk about magnetic field, right? Electric field along the axis would be equal to mu naught. 1 by 4 pi epsilon naught 2p divided by r cube. What about magnetisms? This is just 1 by mu naught by 4 pi 2m divided by r cube. All right. What about equilateral planes? Equilateral plane. This is equilateral plane minus. This is minus mu naught 4 pi m cubed. Then what about torque, right? How much torque it experience? Torque experience is going to be P, right? P cross E. What about torque experience? M cross P. What about potential energy store? Minus P dot E. What about potential energy store? Minus M dot B. So these are the cylinder, right? So everything's, so that means this is how electrostatic is very much related to magnetisms. All right. So this is just for your information, right? And now what I would like to do is arc magnetisms. Arc magnetisms. So we say that just now when I did the introduction parts, the significance of arc magnetism. So maybe in your lower class you might have studied a little bit about arc magnetisms. Here also we are going to study a little, not so detailed about arc magnetisms, right? So the topic is a little complicated. So we say that our arc act as a giant magnet, and which produce a magnetic field, right? So this is what we have. So this is a bar magnet, and this is our arc acting like a bar magnet. So this is the magnetic north, this is the magnetic south. Why? Because when we keep a bar magnet and allow freely suspended on Earth's surface, you find the bar magnet north tend toward the north, bar magnet south tend toward the south. So therefore, I call this as a magnetic north. I call this as a magnetic south. All right, I call this as a magnetic. Conventionally, I am calling it as a magnetic north, magnetic south. So how did you give a name like north and south? Bar magnet north is tending toward north side, so therefore it is called a magnetic north. Bar magnet south tends toward south, we call it as magnetic south. This is how we have given it. So this is what we talk about. So the Earth behaves as a magnet with the magnetic field, approximately magnetic field pointing from geographical south to the north. When the bar magnet is freely suspended, it points in the north-south direction. The tip which points to the geographical north is called the north pole, and the tip which points to the geographical south is called the south pole of magnet. This is what I explained. So there is a repulsive force when north poles or south pole of two magnets are brought close together. Conversely, there will be attractions. So we cannot isolate. This is just what we have done, right? So now before I do a little detail about Earth magnetism. So first we would like to know about Earth, right? The lines which I think you might have studied this in geography in a lower class. Our Earth, the entire position on our Earth or globe can be shown by two lines. One is called a latitude, other one is called a longitude. And so the position of any places or any point on Earth's surface is defined by a two concept, that is longitude and a latitude. So this is called a latitude. This is called a longitude. So latitude is you see a circle, right? So this is the latitude. All right. When we talk about latitudes, the latitude goes from the circle goes from south and north. This is a circle, right? And the biggest latitude is what we call as the equator, right? So the equator which divides north and south. Equator that divides north and south. So latitude gives you north and south. Latitude gives you north and south. Alright, this is what we do. So equator is the center latitudes, or the biggest latitudes, north and south. Anything above equator is south, north below is south. Alright. And the longitude is a line that runs from north pole to south poles. Latitude or longitude is a line that runs from north pole to south pole. So this is again another circle, right? So therefore, this is what we call as meridians, right? So this tells us about east and west. East and west. So prime meridian is a line which divides out into east and west. East side, west side is all defined by what we call as a prime meridians. Meridian. So this is called meridian, right? Alright, this equator and prime meridian, very important, right? East, west, and then our entire clock, alright, the standard times are based on longitude. Why? Because Earth rotation is like that. That is why it is based on this. So this is the point, very important. Now, having this concept, let me have this, right? The axis of Earth. So now we have two axes: geographical axis and magnetic axis. Geographical axis and magnetic axis. Geographical meridians and the magnetic meridians. That you should keep in mind, right? So the axis of the dipole does not coincide with the axis of rotation of Earth, but is presently tilted by approximately 11.3 degrees. That means geographical magnetic meridians, right, does not coincide with magnetic meridians. So I have magnetic meridians. So the magnetic meridian is defined as a lines that joins between magnetic north and magnetic south. Again, I am repeating. A magnetic meridian is a longitudinal lines that joins between magnetic north and magnetic south. And geographical meridian is a line, imaginary lines or longitudinal line that joins between geographical north and geographical south. So this doesn't coincide, right? The angle is what we call as 11.3 degree, right? So now where is the magnetic north and where is magnetic south? So the position of magnetic north is this. Alright, 79.74 north, and the longitude is 71.8 west, somewhere this side, right, Canada side, right? And then magnetic south, right, is at 79.74 south and 108.22 east, this side it falls, right? So this is what we have. So now I talk about magnetic meridians. Geographical meridian never coincide. So geographical meridian tells you the geographical south and north. Magnetic meridian tells you about magnetic north and magnetic south. This is what I have here, right? This diagrams tells you about arc magnetism, right? So this is arc magnetic north, this is arc magnetic south, and this is geographical meridians, and the angle formed is what we is 11.5 degree, right? So this is what we have. All right. So therefore, what happens is that when we allow magnetic compass to freely suspend, if you allow a magnetic compass to and magnetic compass align in this direction, so therefore it is very close to a geographical north, not exactly coincide, but very close to a geographical north, and this is the south is very close to geographical south. All right, so this is how we try to find position, right, with the help of magnet. So the magnet will not give you exact north and exact south, but approximately doesn't make huge difference. So this is what I have. This is another diagram. Okay. Now having this, I would like to divide arc magnetism into a few more components. So arc magnetisms divided into three important concepts. We say the total arc magnetic field. Alright, total arc magnetic field, and that total arc magnetic field can be resolved into the vertical components and horizontal components. Vertical component and horizontal components. So the magnetic meridians, right? Magnetic meridians is nothing but horizontal component, horizontal magnetic component. That you should keep in mind, right? So normally the compass which we use for finding positions tells you only horizontal magnetic components. So since you are on an earth surface, you need to know only a horizontal surface, and north pole and south poles are nothing on a horizontal surface. Alright, that you should keep in mind, right? So total arc magnetic fields, and then we will be talking about angle of declinations and angle of D. These five concepts are very important, right? So having this, now again repeating, right? The direction of longitude circle, right, determines the geographical north, and again a repetition, right? So I will start from here. The vertical plane which passes through an imaginary line joining the magnetic north and magnetic south is what we call as magnetic meridian. So in a way, I say a line that joins the magnetic north and magnetic south is what we call as magnetic meridians, right? So therefore, this is very important, right? This is very important. So a magnetic needle which is free to swing horizontally, that you should allow it to swing horizontally, and would then lie in a magnetic meridian. So every time this lie in a magnetic meridian, and that's since the magnetic meridians connects magnetic north and magnetic south, so you could know where is magnetic south, where is magnetic north. Oh, this is very important, right? This speaks a lot, right? A magnetic needle which is free to swing horizontally would then lie in the magnetic meridians, and the magnetic north pole of a needles would point towards the magnetic north, and the south pole of a magnet point towards magnetic south. So this is what we call, right? And therefore, now since the magnetic meridians and the geographic meridians doesn't coincide, so it makes some angle, right? This makes some angle. So this angle, what I'm going to talk about, is called angle of declinations. So thus, the angle formed between the true geographical north and the north shown by a magnetic compass. All right, compass needle which is used to locate the positions, right? And this angle is what we call as magnetic declinations. So the declinations, so this is what we call, right? This is angle of declinations. So angle of declination is defined as the angle formed between magnetic meridians and magnetic geographical meridians. So at any point on our surface, there will be one line tending toward the magnetic north and magnetic south, other line tending toward magnetic geographical north and geographical south. So you will find some angle, right? This angle is what we call as angle of declinations. Alright, and one very important is greater at a higher, the declination is greater at higher latitudes and smaller at equator. So at equator, you would see a less, smaller angle of declinations. So this is what I will tell you, right? So if you put here and tends greater toward this, so the angle of declination is more. Here at equator, the angle of declination is least. So angle of declination is least at the equators and maximum at the two poles. Maximum at the two poles. That's the reason, right? And then, now this is very, very important, right? So now we will talk about total arc magnetic fields. So this is our arc, and I put any point on our surface. Let's say I put a point P on our surface, and this is a horizontal. You see, these horizontals are normally defined by a tangent, right? So this is a horizontal components HE. If it is not clear, this is HE. And what about vertical? So vertical has to point toward the center, right? So when you join these two, and this is going to become a total arc magnetic field. This is going to become a total arc magnetic field. This is going to become total arc magnetic field. This is how you get it, right? So total arc magnetic field is normally defined by deep compass. When you return, we will discuss this in our lab, right? So this is our three-dimensional. I will show you this. This is a three-dimensional diagram, right? This is a point P. This is a point P, and here you have this is the north pole. All right, and this is total arc magnetic field, and this is the vertical arc magnetic field, and this is the horizontal arc magnetic field. All right, horizontal arc magnetic field. Now I say that this angle is what we call as angle of declinations. This angle is what we call as angle of declination. Now I would like to define another angle called angle of dip. So angle of dip is defined as the angle formed between magnetic horizontal arc magnetic field and the total arc magnetic fields. All right. So this is what we call angle of inclinations. All right, angle of inclinations. Right. So angle formed between magnetic meridians and the total arc magnetic field is what we call as angle of inclination or angle of dip, right? The dip angle is angle that the total arc magnetic field BE of arc makes with the surface of arc or horizontal component arc magnetic field. The total arc magnetic field at P can be resolved into horizontals and verticals. Alright, and that angle I. So now what we talk about is angle of G's. Angle of G's. All right. Okay, now then now we would like to do how to define, right? How to define this, right? So look at here. When I say a sine I is deep angles. Sine I is what we define as ZE divided by BE. So therefore, vertical arc magnetic field component is defined as this. Alright. Then a cos I, which we define as HE, alright, HE, and then BE, and then HE is defined as BE cos I. And what about relation between these two, right? Tan I is how we relate ZE and HE. This is how you relate between different arc magnetic field components. Alright. So these are the example different diagram I have. So this is arc magnetic meridians plane, right? So you cut arc in a longitudinal way. This is the double figure, and this angle is what we call angle of declinations, and this is angle of inclination or angle of deep. These are the example, right? Different diagrams I have. This is what I have. Look at here. So look at here. So this is what we have. Now these are the magnetic field lines. These are the magnetic field lines. Now what I would like to discuss here is how magnetic fields, how angle of declination, angle of deep vary from equator to pole. At equator, angle of deep is going to become 0. Why? Because there won't be any, the angle of total arc magnetic fields is almost along horizontals. If a total arc magnetic field is almost along horizontals, then there is no angle between horizontal arc magnetic field and a vertical arc magnetic field. So therefore it is almost 0 at equators. The angle of deep at equator is almost 0. So what about pole? When you talk about pole, it is vertically in, right? When you at the two poles, total arc magnetic field is almost along verticals. If it is total arc magnetic field is almost along a vertical means then it makes 90 degree. So at the two poles, angle of inclination, angle of deep is 90 degree. So this is one, and this diagram also tells us, right? This diagram also tells us, right? So almost horizontal. This is equator. This is equator, almost horizontal, right? Yes, this is a very interesting diagram. So that this diagram tells us, right? This is horizontal. This is total arc magnetic field. This angle is called angle of deep, right? This is a deep angle. This is deep angle. This is the total arc magnetic field. This is the horizontal arc magnetic field, and this is the angle of deep. Now this is arc, right? So at equators, magnetic fields, the total arc magnetic field is almost along horizontal. This diagram tells us. Total arc magnetic field is almost along our horizontals. So therefore, angle of deep is going to become 0, right? What about this? Alright. So at the pole, alright, deep angle is maximum. It's almost 90 degree, right? So this is what we have. 90 degree, right? And one more, the concept here is, if you bring a magnetic needle at the pole, the deflections, this will not align in a particular pattern, right? This will align in randomly. Why? Because there is no horizontal magnetic field. If there is no horizontal arc magnetic fields at two poles, so therefore the magnetic compass doesn't align in a particular pattern, right? So this is again very important. So how do you know that you are at a pole? A magnetic compass doesn't work at 2 poles. This is what I have. This is what we call a deep compass. We will show you in a class. And now last part is what I'm going to talk about is magnetization and magnetic intensity. So this is entirely about matter, right? Magnetisms, right? Magnetisms, right? So first I would like to define what we call as magnetizations. So magnetization is a vector quantity, or M is a magnetizations. And before that, maybe last time we say that the revolving electron acts as a magnetic dipole, and this is the very origin of magnetic property of matters. Alright, the very fundamental origin of a magnetic property of matter is the electron that is going around the nucleus, and a revolving electron acts as a magnetic dipole. So therefore this we should keep in mind, right? So therefore in matter, N is the magnetizations. N refers to our magnetizations, and magnetization is defined as net magnetic moment per unit volumes. This is what we have. Net magnetic moment per unit volumes. So magnetization is again a property, right? So magnetization is defined as a net magnetic moment per unit volume is what we call as magnetic intensity. I can put here net also. And what about net magnetic moments, right? Net magnetic moments is defined as magnetizations multiplied by volumes. That's correct. Alright, now I consider a solenoid. So we are going to talk about the property of magnetic property of matter. Right. When we talk about a solenoid, I have a solenoid of n number of turns getting a current I. Alright. And then in so magnetic field without any mediums is going to be mu naught Ni. This is a magnetic field inside solenoid. Magnetic field inside solenoid. Alright. Now what I'm going to do is I put something in a magnetic fields. Interior of a solenoid is filled with some materials. Therefore, I just say now total R magnetic field is total magnetic field inside solenoid is going to become. Alright, this is what I have. So this is the magnetic field due to a solenoid. This is magnetic due to a magnetization. Magnetic field due to magnetizations. Magnetic field due to solenoid. Alright. Now look at here. So this what we talk about is this is directly proportional to magnetizations. If the metal is highly magnetized, so therefore magnetic field would be greater. Alright, so therefore this is proportional to this, and then I'm going to put a constant, that is magnetic permeability in the vacuums. This is one thing. And then I would like to define one more quantity called magnetic intensities. Define magnetic intensity, that is what we call as H. How do you define H? H is equal to total B divided by mu naught minus n. Why? Because physically m and h are equivalents. M and h are physically they are same quantity. M is for magnetic. M is for magnetism due to matters, and H is magnetic intensity that is due to solenoids. The only difference is M is for matter or bar magnet, whatever, and H is for solenoid. This is for bar magnet, whatever, right? Bar magnet or iron, whatever, right? Or irons. And this is solenoid, right? So therefore what we have is B is equal to, I just put vector, these are vectors. B is what we call as mu naught H plus H. So now look at here. What is this is equal to mu naught H by M. So now these two are related. M and H are related. If there is no magnetization, if there is no magnetic intensity, magnetization would be zero, right? So therefore, magnetic intensities, magnetization is proportional to magnetic intensity. All right. Magnetization is proportional to magnetic intensity. So therefore, I just say this is equal to constant is what we call as magnetic susceptibility. This is what we call magnetic susceptibility. Magnetic susceptibility. This is called magnetic, which has no unit. Which has why? Because these two physicals are same. So therefore, this is a constant which has no unit. This is a constant which has no unit. All right. So I substitute. So this is the physical property. This is what we call as a physical property of matter. This is what we call as physical property of matter, right? So I substitute this H plus mu H. So finally I got this. So I just say that I define that this is what we define as relative magnetic permeability. This is what we 1 plus chi is what we call as relative magnetic permeability. So therefore B is going to become mu naught mu r H. And this tells about magnetic property of matters. Magnetic property of matters. This tells why? Because this is the constant, right? This is the constant which tells about magnetic property of matter, and this is also a constant that tells about magnetic property of matter, right? Again, I am going to write mu naught mu r is what we call as mu. Mu naught mu r is what we call as magnetic permeability of mediums. All right. So therefore, relative permeability is equal to mu divided by mu. This is the point. Alright, so I have given a few terms. This is very important terms, and this is very important terms. This is again very important terms, right? So this is what I have. So now, now to do a small problems. So this is frequently come in exams. That is. We talk about magnetic pole strength, right? Pole strength. Pole strength is how we define pole strength is defined by magnetic moments. Pole strength is defined by area, right? Pole strength is defined by area, right? So normally I say that magnetic moments is what we call as magnetizations multiplied by area multiplied by length, right? And a pole strength is defined by area. And a total magnetic moments, I say a total magnetic moments is defined by a volumes, Alright, now in exams you may come across like I have a bar magnet like this, north pole, south pole. This is called a transverse cut. If I cut this magnet into two equal halves and along a transverse, what about pole strength? Alright, so in this case pole strength reduced to half. And what about total magnetic moments, right? Total magnetic moments reduced to half. This is 1 point. Now I have a bar magnet like this. This is a horizontal cut. I'm sorry, this is a horizontal cut, not transverse cut. This is a transverse cut. This is a lateral cut. This is a lateral cut. This is a transverse cut. When I do a transverse cut, pole strength remains same. Pole strength remains same. Why? Because area remains same. What about magnetic moments? Magnetic moment reduced to half. That you should keep in mind. Very important. Alright. Alright. Now having this, this is not there in our, this has been deleted from syllabus this year, right? However, I'll do a little bit on this. Magnetic property of metal. So the entire magnetic property of a metal is defined by this term, right? Magnetic susceptibilities, relative magnetic permeabilities, and then magnetic permeabilities. Alright, these three terms, right? So for dimagnets, this is for diamagnet. Magnetic susceptibility is negative. Alright, so this is not for exam, right? Just for your understanding, right? And the relative magnetic permeability for diamagnet is less than 1. And then more than 0. Alright? Sometimes it is perfect diamagnet. This could be like this. Perfect diamagnet. So for paradiamagnet, this is going to be 1, 0. This is epsilon is a small value, right? So therefore, this is going to become more than 1 plus. And what about ferromagnetisms? This is going to become much more than 1s. Then, so these are the points, right? So this is how. So the entire magnetic property of metal is defined by these three terms. All right. So since this has been deleted from our syllabus, so we don't need to study this, right? Up to this. So with this, I have finished chapter number 5. Okay. Thank you.